In October 2025, the universe blinked. Interstellar comet 3IATLAS, an object from beyond our solar system, passed behind the Sun and vanished without explanation. When it reappeared, it was changed, dimmer, fractured, almost rewired. And in its absence, strange things unfolded. Radio whispers, missing data, a solar flare that seemed to answer its approach. Then, as Atlas faded, another comet took its place. Bright, perfect, distracting. What if that wasn't coincidence but choreography? Tonight, we follow the trail that science can't explain and history tried to erase. From erased telemetry and synchronized pulses to the theory that something watched back from behind the Sun. Was 3IATLAS destroyed, transformed, or deliberately hidden? This is the story of a visitor that defied every law we know, and the silence that followed when the evidence itself began to disappear. Or a brief, shimmering window of time, the universe itself looked away. As 3IATLAS approached its perihelion, the point closest to the Sun, something remarkable happened. Tracking systems across NASA, ESA, and independent observatories all reported the same thing: a sudden drop in signal, a flicker in telemetry, and then nothing. The comet vanished. Officially, it was solar interference. The glare from the Sun had drowned out the faint reflection of a small interstellar body. It happens all the time, scientists said. But this time, the blackout wasn't smooth. It came with timing anomalies, data frames out of sync, signal delays measured in milliseconds that couldn't be explained by the Sun's position alone. For days, the comet hid in the one place where no telescope could follow. And when it came back, it didn't look the same. That vanishing act became more than a data glitch. It was a question. What happened behind the Sun? Flare, hole, or coincidence? Right when 3IATLAS disappeared, the Sun itself changed character. A massive coronal hole tore across its equatorial region, an open wound spewing streams of charged particles directly toward the inner planets. Simultaneously, a flare erupted from the opposite hemisphere. To casual observers, these were separate solar events. But the timing aligned almost perfectly with the comet's passage behind the Sun. Solar physicists noted it as coincidence, yet others wondered whether the two phenomena were connected. Could Atlas's ionized tail have interacted with solar magnetic fields, triggering a chain reaction? It sounds impossible, an icy body influencing a star. But 3IATLAS isn't like any other comet we've seen. It's interstellar, carrying materials forged around another sun entirely. If its magnetic composition was foreign, nickel-heavy, iron-poor, it might not behave like a typical comet at all. And during perihelion, where solar wind pressure peaks, even the smallest electromagnetic irregularity could cause effects we've never modeled before. Last light before the curtain, a strained spectrum. Moments before it vanished into the Sun's glare, spectrometers captured a strange mix of emissions. Cyanide, a known cometary gas, spiked higher than expected. Water vapor surged in short, chaotic bursts. But the most puzzling signature was metallic. Nickel without iron, a combination that shouldn't naturally occur in large quantities. If the readings were accurate, this was no ordinary iceball shedding dust. It was an active reactor of sorts, heating, venting, changing as it neared the Sun. A few scientists suggested that internal crystallization could have caused volatile expansion, cracking the comet open from within. Others whispered about a switching event, as though something inside Atlas had reached a temperature threshold and activated. And then came silence. Every telescope pointed at the Sun's edge lost sight of the object simultaneously. No fragments, no reflection, just a void like a door closing in space. Ghosts in the noise, radio whispers, and missing frames. During that blackout, deep space radio monitors began picking up something odd. Bursts of static, low-frequency pulses that didn't match solar radio emissions. At first, engineers blamed interference, perhaps from the solar storm. But when those signals were cross-referenced with data from other observatories, faint alignments appeared. The pulses followed the comet's last known trajectory. The transmissions were brief, too structured to be random, yet too inconsistent to decode. A few frames of data from ground-based radar systems were corrupted in the same hour, replaced by digital noise patterns eerily similar to Morse code. Coincidence, possibly. But when the sun was flaring violently, such interference should have been white noise, broadband, chaotic. This was something else. Some began to speculate that 3IATLAS wasn't just reflecting sunlight. It was interacting with electromagnetic fields in an active way, perhaps releasing charged particles in rhythmic bursts, or, in the wilder theories, responding. Reappearance with a limp, brightness, tail, and track. When the comet finally re-emerged from behind the sun, it was different, dimmer. Its coma, once vibrant green, had lost intensity, and its tail had warped into an asymmetric curve. NASA's solar orbiter noted small but measurable trajectory deviations, as though it had been subtly deflected. The object wasn't destroyed, but something fundamental had changed. Some astronomers suggested partial fragmentation. Others blamed outgassing irregularities from uneven heating. But the change in reflectivity, or albedo, raised eyebrows. It was as if the comet's surface had been restructured, melted and refrozen with new properties. Spectral data hinted at compounds not previously detected, like silicates that had been vitrified, glassified by intense heat. And through it all, the timing of its reappearance was off by a few minutes, minor in astronomical terms, but significant when every second of orbital data matters. It had disappeared as one object, and returned slightly altered. The distraction effect. Another comet takes the stage. As Atlas dimmed, another object quietly began to dominate telescope chatter. Comet Lemon. Bright, visible, and conveniently placed for observation. Media headlines shifted. Space agencies redirected instruments. Public attention followed. It was as if the sky had offered a convenient substitute, a new spectacle to draw the gaze away from what had just happened. Those who kept their focus on 3IATLAS noticed that post-perihelion data updates slowed. Some datasets were marked pending re-evaluation. Coincidence, perhaps. But it mirrored a pattern seen before. When one cosmic mystery goes dark, another conveniently lights up. Whether deliberate or not, this distraction effect ensured few looked back long enough to question what truly occurred during those missing hours. And by the time Atlas resumed a stable trajectory, its story had already shifted from anomaly to afterthought. What vanished, the object or the evidence? So what truly disappeared at perihelion, the comet or the truth about it? The simplest explanation is also the safest. 3IATLAS passed too close to the sun's radiation, shedding volatile material and fragmenting partially before stabilizing. The data gaps were technical, just artifacts of a harsh observation environment. But simplicity doesn't erase the peculiarities. The radio bursts, the spectral anomalies, the subtle orbit changes all suggest something happened during that solar crossing we still can't explain. It might have been a physical transformation, a chemical ignition, or even a magnetic resonance triggered by solar proximity. If 3IATLAS carried exotic material from another star system, its behavior under solar stress could reveal physics we've never seen. And if something inside it switched on, even for a moment, perihelion was the perfect place to do it, shielded by the brightest light in the universe, invisible to every eye on Earth. When it vanished, we lost sight of more than a comet. We lost continuity, an unbroken record of an interstellar visitor behaving in ways our models can't fully account for. Maybe that's why, even now, the story feels incomplete. Because in space, a disappearance isn't just the absence of light, it's the presence of something, hiding in the one place no one can look. The moment 3IATLAS slipped behind the sun, the star itself seemed to react. Within hours, a colossal coronal hole unfurled across the solar equator, an opening in the magnetic field where charged particles screamed into space at nearly 2 million miles per hour. From the same hemisphere, an X-class flare erupted, one of the most violent in solar cycle 25. It was supposed to be a routine crossing. Astronomers had seen countless comets pass behind the Sun before, each swallowed briefly by the glare, then reappearing days later, dim but intact.
But not this one.
With Atlas, timing became everything, and timing is what made the entire event suspicious. The flare, the hole, and the disappearance all occurred within the same 12-hour window. Not before, not after, during. The simplest interpretation is coincidence. The Sun's activity, after all, is constant chaos. Flares erupt daily, coronal holes form and vanish in unpredictable cycles. But in cosmic investigation, coincidences that align too perfectly are treated like fingerprints. They demand closer inspection. The flare's signature was peculiar. Its rise and decay times didn't follow the standard curve, flattening midway as though something had interfered with the energy release. Solar physicists noted it but moved on. The anomaly was minor, statistically ignorable. Yet, when data from the Solar Dynamics Observatory was cross-referenced with magnetometer readings, an odd synchronicity appeared, a transient dip, almost like an echo, precisely when the flare plateaued. Could a comet, an object smaller than many asteroids, really alter solar behavior? Conventional science would say no. The Sun's energy dwarfs anything else in the solar system. Yet, for decades, scientists have speculated that magnetic or plasma interactions could occur when highly ionized material crosses the heliospheric current sheet, the invisible, undulating surface dividing the Sun's magnetic polarity. And that's exactly where 3IATLAS was. As it approached perihelion, Atlas followed a path nearly perpendicular to the solar equator, skimming across the current sheet like a pebble skipping a pond. This region isn't just magnetic, it's electric. Plasma currents shift polarity every 11 years, and during solar maximum, the sheet becomes turbulent, unpredictable. If the comet's tail contained conductive dust or metallic particles, nickel, for instance, it could have acted briefly as a moving filament, disturbing local fields. That disturbance might have caused the Sun's plasma to behave differently, warping the flare's rise or amplifying the coronal hole's expansion. It's speculative, yes, but magnetohydrodynamic simulations have shown similar behaviors when small conductive bodies pass through dense plasma streams. The energy exchange doesn't come from the object itself, but from how it redistributes the Sun's existing current. Imagine the Sun as a vast electrical engine and the comet as a passing spark plug. Momentary, tiny, yet enough to cause a flicker in the system. Not everyone bought the idea. Many experts insisted that the timing was simply bad luck. The flare and coronal hole were independent, predictable outcomes of solar cycle 25's peak. But a few researchers noticed something the public never saw: the flare's shape. In most high-resolution ultraviolet imagery, solar flares bloom like blossoms, radiating outward evenly. This one had a twist, literally, a helical formation that rotated slightly clockwise, as if wound by an unseen torque. Such motion had been observed only once before, in 2003, during the so-called Halloween
storms, when Earth's magnetic field took its hardest hit in modern
history. Those storms were also preceded by the arrival of a dense plasma filament, one that had carried traces of cometary debris. That historical echo wasn't proof, but it was enough to reopen the question: could Atlas's approach have triggered, or at least modulated, the solar outburst that accompanied its disappearance? Then came the missing frames. When the flare reached its peak, the Solar and Heliospheric Observatory, SOHO, briefly lost visual telemetry. Engineers attributed it to corrupted imaging buffers due to particle noise. The images resumed minutes later, but 3 frames were gone. The lost interval spanned exactly when Atlas should have entered the outer corona. The replacement frames, reconstructed from secondary feeds, looked off. Brightness gradients mismatched, and the comet's projected position was conspicuously clean. No streak, no artifact, nothing. It was as though the region had been digitally scrubbed, either by processing error or something more deliberate. That's when conspiracy theories took root. Some argued that the flare had been artificially exaggerated in post-processing to conceal the comet's proximity. Others believed the data gap hinted at a classified observation, a signal transmission perhaps, or an interaction too sensitive for public release. NASA denied it, of course. Yet the official explanation for the lost data changed 3 times. In 1 week, from buffer overflow to magnetospheric interference to software realignment during event compression. The inconsistency didn't help. Meanwhile, on Earth, auroral activity spiked beyond expectation. Normally, X-class flares take 48 to 72 hours to influence Earth's magnetic field. But in this case, minor disturbances were registered within 14 hours, too soon for conventional solar wind travel times. That anomaly led to one of the most intriguing theories, that the flare wasn't just an outburst of light, but also a directional ejection, a guided plasma jet, almost like a pulse aimed along the plane where Atlas had vanished. If true, that could mean the Sun was responding to something in that region, reacting rather than randomly erupting. The possibility bordered on heresy in astrophysics, but data from the Parker Solar Probe lent quiet support. While passing near the inner heliosphere days later, Parker detected residual plasma waves that shouldn't have existed, ripples of charged particles moving in a cohesive pattern, not the chaotic spray expected from a normal flare. The pulse seemed to emanate from a point just behind the Sun, exactly where 3IATLAS had been. When Atlas reappeared days later, it carried with it the fingerprints of that storm. Its coma was enriched with ionized oxygen and traces of silicon, elements that could only have been stripped from intense radiation exposure. Yet curiously, its nucleus showed no thermal scarring. It had endured heat that should have melted it, and somehow it hadn't. The explanation? Unknown. Some suggested that the comet's outer shell was composed of complex silicate lattices, heat-resistant minerals found in exoplanetary debris disks. If true, it would mean Atlas came from a system with vastly different chemistry, possibly where nickel compounds dominate instead of iron. That unusual material might have absorbed and redistributed the Sun's energy, creating a temporary electromagnetic shield around the nucleus. In simpler terms, the comet didn't burn, it resonated, and that resonance could have interacted with the Sun's magnetic fields, feeding energy back into them. There's
An eerie symmetry in the data, the flare that
coincided with Atlas's disappearance released just enough energy to generate a global geomagnetic storm, but not enough to damage satellites or disrupt communications. It was the perfect intensity to drown a weak signal in cosmic noise without raising red flags, almost like the universe turning on a blinding light just long enough to hide something moving behind it. That's where the more speculative theories begin. Some astrophysicists whisper about resonance events, moments when two magnetic bodies interact across a plasma medium, amplifying each other. If Atlas carried a strong dipole field, unlikely but not impossible, it could have momentarily locked with the Sun's local field lines, creating a mutual surge that triggered both the flare and the coronal hole simultaneously. Such a phenomenon would blur the line between natural physics and something deliberate. Because if that lock happened, even briefly, information, energy, particles, maybe more, could have transferred. To the public, the flare was just another beautiful solar storm, its footage plastered across news sites. But to those watching 3IATLAS, it felt staged, an eruption that came right on cue, erased every trace of visibility, and left behind data gaps no one could fully explain. And the timing, always the timing, refused to fit coincidence neatly. When the flare began, Atlas was positioned behind the sun's limb. When it ended, the comet's projected path had shifted slightly. In celestial terms, that's like a coin disappearing behind your hand and reappearing half an inch off-center. Something had nudged it, however gently. The story that started with a blackout now had a pulse, a heartbeat buried in radiation. Maybe it was the sun itself answering back to an intruder from another system. Or maybe, for a few brief moments in October 2025, something used the sun, its energy, its chaos, as cover to do something we weren't meant to observe. Whatever the case, one truth remains. The moment 3IATLAS passed behind the sun, our own star blinked, and when the light returned, nothing looked quite the same. The final images of 3IATLAS before it vanished behind the sun tell a story few noticed at first. In those last frames, captured by NASA's Solar and Heliospheric Observatory, the comet appeared to brighten, but not in the usual way. Its glow didn't bloom outward like a flare reflecting sunlight. Instead, it pulsed in rhythmic intervals, as if breathing. At first glance, it looked like pixel interference. But spectral analysis told another story. The light coming from Atlas didn't match known cometary emission profiles. Typical comets display a predictable mix: oxygen and hydrogen from sublimating ice, traces of carbon dioxide, cyanide bands, maybe a few metallic traces. Atlas's spectrum was stranger: sharp spikes where there should have been smooth gradients, irregular drops where emission lines should have risen. Scientists called it strained, a word that quickly became synonymous with the object itself. It was as if the comet were tearing at the limits of its own chemistry, forcing reactions that didn't belong in our solar chemistry at all. And just before the blackout, something impossible flickered across the data: nickel emission without a corresponding trace of iron. To the untrained eye, that sounds trivial, but to astrophysicists it's like hearing a piano play without strings attached. Nickel and iron are twin elements, born together in stellar cores, fused in supernovae, and scattered across space as inseparable partners. Wherever you find one, you find the other. Yet here, 3IATLAS defied that cosmic rule. Nickel, yes.
Iron? No. It wasn't the first time interstellar objects had broken expectations.
Oumuamua had refused to emit a visible tail. Borisov had carried cyanide in concentrations bordering on toxic. But Atlas was in another category. Its spectral fingerprint actively changed the closer it came to the sun, as if responding, evolving, or shielding itself from the heat. When astronomers overlaid the final spectra from the Lick Observatory and the European Southern Observatory, they noticed something even more unnerving. The emission peaks weren't just chemical, they oscillated. In other words, they moved. That shouldn't happen. Chemical signatures are static unless the object's composition itself is fluctuating at extraordinary speeds, something we've only ever seen in artificially modulated sources, like communication lasers or plasma containment experiments. Could it be an instrumental error? Possibly. But the oscillation was confirmed by multiple observatories on opposite sides of the planet, all within the same 2-hour window before Atlas entered the sun's blinding halo. The signal wasn't random. It was consistent, periodic, like a heartbeat. The public never heard about this in detail. The official summary buried it under data normalization artifacts due to solar glare. But buried in technical supplements shared between observatories, quiet discussions began, emails exchanged under subject lines like pulsed reflection behavior and anomalous Nephi deviation. Some of those correspondences, later leaked to astronomy forums, painted a far stranger picture. One analysis suggested that the oscillations were too clean to be thermal. The comet wasn't just heating up and cooling down, it seemed to phase through states of emission, as though its surface were being periodically ionized. That's the kind of behavior expected from controlled plasma or magnetic,
modulation, not natural outgassing. Another
noted that the spectral lines clustered around a frequency band, suspiciously close to the radio emissions, produced by Earth's own ionospheric resonance. It was probably coincidence, but the alignment was uncanny. It almost looked like the comet was tuning itself to frequencies native to our planet's magnetic field. If that were true, it would mean the object wasn't just reacting to the sun, it was responding to the solar system itself. In one of the last usable images, frame 2784 from the LASCO C3 camera, the comet's tail flares suddenly, then twists.
It's subtle but visible, like a spiral tightening.
Analysts later compared it to a torsion wave, a pattern that occurs when magnetic flux lines are wound around a moving core. This twisting pattern has been observed in one other natural setting, in electromagnetic simulations of plasmoids, self-sustaining plasma structures capable of maintaining internal magnetic coherence. In theory, such forms could exist in nature, but we've never seen one in motion before, let alone around a solid nucleus. If ATLAS was generating its own magnetic sheath, it could explain the irregular light emissions. The nickel signature might have come from an active magnetic interface, nickel ions responding to changes in the sun's magnetic field rather than passive sublimation. In short, ATLAS might have been alive magnetically, a plasma organism in the making, or at least behaving like one, but here's where the data gets even stranger. Just before the final signal dropout, instruments picked up a burst of ultraviolet emissions from the comet's core, so brief it lasted less than a second. The wavelength pattern didn't match any known solar scattering phenomenon. Instead, it aligned with emission lines typically associated with ionized xenon and neon, rare gases found in fusion experiments, and, oddly enough, spacecraft propulsion. No one expected a comet to produce xenon light. It was dismissed as a reflection from solar activity, a backscatter anomaly. But when researchers at the University of Bern cross-analyzed the timing, they found that no solar flare had occurred at that moment. The light came solely from ATLAS's vector, and only once after that the object dimmed, as though it had expended something or completed something. Within minutes, its spectrum collapsed into a featureless wash of reflected sunlight. Then the data stopped entirely. What followed was an eerie silence, 5 days without a single confirmed sighting. When the comet emerged from behind the sun, its spectral profile was radically altered. No cyanide, no water bands, no nickel, just a weak continuum of light, colder and flatter than before. Some said it burned out, others said it metamorphosed. But the missing interval, the curtain period, as astronomers began calling it, remains one of the most heavily debated gaps in modern cometary science. What could make a body emit artificial-like oscillations then go completely silent? Some speculated that ATLAS's core underwent a phase transition, a moment when extreme heat or magnetic compression caused its materials to reorganize into a new crystalline or metallic lattice. Such a structure might have reflected light differently, explaining its changed spectrum. Others suggested something more speculative, a reaction between interstellar compounds and solar radiation that triggered an unknown process, a form of self-repair or even replication. One theory, quietly circulating in fringe astrophysics circles, proposed that ATLAS wasn't a comet at all, but a fragment of a larger interstellar construct, perhaps an ancient probe or the remains of something that once was. Its strained spectrum was simply the dying pulse of an alien technology encountering the raw power of a star. It's a wild idea, but the data gaps leave room for it. There's a subtle irony here. The last time humanity saw something like this, an object emitting unexplainable frequencies before disappearing behind a star, it wasn't a comet. It was Voyager 1 when its signal briefly distorted after passing through a solar radio storm in 2014. Engineers blamed plasma density, But for 3 minutes, Voyager's transmission carried repeating harmonic tones, a pattern that's still archived but never decoded. Now, a decade later, an interstellar visitor mirrored that same behavior. 2 signals, 2 disappearances, both swallowed by the same sun. When researchers plotted the light intensity from Atlas's final frames, a strange rhythm emerged, peaks and troughs spaced at almost exact intervals of 4.2 seconds. That number doesn't mean much until you realize it's nearly identical to the oscillation period of the sun's own low-frequency acoustic waves, the so-called heartbeat of the sun. Was the comet resonating with the star itself? If so, that would make 3IATLAS not just a passive traveler, but a participant, a foreign body adjusting to the solar system's pulse. And perhaps that's what the strained spectrum really was, not light under stress, but communication under pressure, a dialogue, however brief, between the sun and something from beyond it. When the blackout ended, the conversation stopped.
Atlas returned, dim, altered, silent.
But traces of that moment, the flickering spectra, the vanishing nickel lines, the ultraviolet flash, linger in the archives like ghost notes in a song. Every explanation offered so far feels partial, as if missing a page.
And maybe that's fitting.
Some stories are written not in what we see, but in what disappears. The last light before the curtain wasn't just data, it was a warning of something beyond comprehension. A cosmic whisper that said, "I've seen your sun."
And now it's seen me.
When the light vanished, the silence should have followed, but instead there was noise. Not the kind of noise engineers dismiss as static. This was something else. Subtle, rhythmic, and persistent, a low hum threaded with faint pulses that appeared across radio spectrograms from observatories on 3 continents. It wasn't constant. It came in short, staggered bursts, sometimes minutes apart, sometimes hours. At first, no one connected it to 3IATLAS. After all, the comet was invisible, lost behind the solar glare. Every telescope in the world was effectively blind. But a few researchers noticed a peculiar coincidence. The bursts arrived almost exactly when deep space monitoring stations switched between data channels to avoid interference from the sun, as if the signal knew when to speak, when no one was listening. The first detection came from the Parkes Radio Telescope in Australia. A graduate researcher running background calibrations noticed what she described as ghost traces, tiny amplitude spikes at 1420 MHz, the hydrogen line, the most fundamental frequency in the universe. Every radio astronomer knows it. It's the channel of creation, the whisper of neutral hydrogen across deep space. But these spikes weren't natural. They were narrow, precise, and repeated at oddly regular intervals, 423 seconds apart. That number, again, the same periodicity found in Atlas's flickering light spectrum before it vanished behind the sun. To anyone else, it would have looked like random data noise. But pattern recognition software caught the repetition and flagged it as non-random emission. Parkes logged it, filed it under unknown interference, and moved on. Yet over the next 72 hours, 3 other observatories, one in Chile, one in South Africa, and one in the Canary Islands, reported the same signal.
Same pattern.
Same frequency band. Same timing. The signal wasn't global, it was coordinated. Meanwhile, the Solar and Heliospheric Observatory, SOHO, was struggling to recover its imaging feed. Engineers noticed that several frames in the LASCO C2 camera had been corrupted. Overexposed patches, streaks of light shaped like thin arcs. It looked like cosmic ray interference, the kind that happens when high-energy particles strike the CCD sensor. But when they ran the error check, they found something that shouldn't have been there. Each corrupted frame contained repeating data blocks, like identical digital fingerprints stamped into the static. When the bytes were converted into binary images, faint waveforms appeared, ripples that mirrored the radio pulse pattern. Coincidence again? Or were the radio bursts somehow embedded into the visual data itself? Someone at ESA's data integrity team made a chilling observation. The corrupted frames occurred exactly 1.3 seconds before each radio pulse registered on Earth. The same sequence, just offset in time. It was as if something near the sun was transmitting, and the solar flare's electromagnetic storm was carrying the echoes across multiple channels, optical,
magnetic, and radio, all converging into one distorted whisper. Then came the deep space monitors.
NASA's Deep Space Network, DSN, in Goldstone, California, picked up unclassified transient noise across its Mars tracking band. Normally, such interference comes from solar plasma scattering, but this time it carried modulation, rising and falling tones embedded in the static. Like someone tapping a code inside the chaos, technicians tried to decode it, running it through standard fast Fourier transforms and pattern filters. The signal refused to fit any terrestrial template. When sped up 100x, it resembled a voice, an eerie, almost mechanical rhythm of tones and pauses, alternating between silence and sudden harmonic surges. One analyst described it best. It sounded like an echo of something too far away to hear.
Stretched thin through time, what unnerved the most wasn't what it said, but when it spoke.
The bursts only appeared when Atlas was geometrically aligned with the Sun and Earth, a perfect line of sight through the solar plasma. As if the object, or whatever it had become, was using the Sun as a carrier wave. By day 3 of the blackout, the bursts grew stronger. Amateur radio astronomers began reporting strange interference on long-wave frequencies, especially during night hours.
Static that pulsed like a heartbeat, faint whispers buried in the hum.
Some claimed they heard syllables, half-formed sounds that felt intentional. YouTube filled with speculation, alien signals, solar modulation, data tampering. NASA issued a short statement. No extraterrestrial signals detected. Observed emissions consistent with known solar radio bursts. But professionals knew solar bursts don't repeat every 4.2 seconds, nor do they mimic structured waveforms. Something was modulating the interference, something rhythmic, and every time the burst ended, the radio silence felt colder, like a vacuum reclaiming its space. Meanwhile, an independent research group in Norway cross-referenced the timestamps from the Parkes, Goldstone, and Soho datasets. When aligned, the pulses formed a repeating pattern that resembled binary. Not clean binary, but analog drift, as though the signal were decaying across layers of interference. When converted into grayscale imagery, it produced a haunting visual, concentric rings with a bright central point, surrounded by faint radial streaks. To the untrained eye, it looked like an eye, the eye of the sun itself staring back through noise. The group named it the Atlas Pulse. Of course, the mainstream community dismissed the pattern as pareidolia, the brain's tendency to find meaning in randomness. But even skeptics admitted something curious. The pulse data contained harmonics at frequencies corresponding to the Schumann resonance, the global electromagnetic heartbeat of Earth. That shouldn't have been possible. The signal originated millions of kilometers away, beyond the sun's corona, yet somehow resonated with Earth's atmospheric frequency. It was as if the whisper from the void had found our frequency. On the 4th day, the data gap widened. Soho's logs for a 6-hour window were missing entirely. When queried, the team blamed telemetry loss due to proton storm saturation. But the timestamps didn't match any recorded solar storm. Inside NASA's archival dataset, that gap still exists, a chunk of history scrubbed clean. Those who've seen the original logs before the patch say the frames contained something remarkable, a faint outline crossing the sun's limb, shaped not like a comet, but like a cluster, multiple luminous points moving as one. It lasted less than 10 seconds before the data glitched into noise, and then came the burst. Stronger than before, longer, as if something was saying goodbye. After that, silence. When 3IATLAS finally reappeared from behind the sun days later, its radio signature was gone. The spectrum flattened, its brightness faded. Whatever had been transmitting or resonating was now dead quiet. But the aftermath lingered. Infrasound detectors across the planet registered faint electromagnetic pulses days after the event, bouncing through the ionosphere in harmonic chain. Some were too weak to notice. Others caused minor power fluctuations in observatories using sensitive magnetometers. Even today, some researchers quietly admit that those anomalies never fully disappeared. Every few weeks, faint echoes, pulses matching the 4.2-second rhythm, still appear in deep space listening arrays, not always from the same direction, not always at the same frequency, but unmistakably shaped by the same underlying signature. It's as though the signal keeps bouncing, reflected, refracted, distorted, but never fully gone, like the dying ring of a cosmic bell still vibrating long after it was struck. Some believe it was plasma interference, a natural resonance between the comet's ionized trail and the sun's electromagnetic field. Others think it was something more deliberate, a broadcast, or even a memory, because when the missing frames were reconstructed using partial data recovered from secondary caches, a chilling discovery surfaced. The pixel gradients weren't random. The pattern of missing light encoded a shape, not a face,
not text. Something abstract yet purposeful. Spiral. The same spiral seen twisting through Atlas's tail in the final frames before it vanished. A spiral that
looked eerily similar to magnetic field simulations and to the geometry of a certain ancient petroglyph. Found across multiple continents, a double-armed vortex carved by civilizations that never met. Coincidence? Or continuity? In the end, we may never know. The missing frames remain redacted, the raw data inaccessible. Officially, the Atlas pulse doesn't exist. Unofficially, hundreds of archived backups across independent observatories preserve the anomaly, shared quietly among scientists who refuse to forget. The last surviving signal log from Parkes ends abruptly, mid-transmission. The final amplitude spike before the silence carries a curious timestamp: 3IATLAS 2025 10-09T2242 OZ. Exactly the moment it passed behind the sun when decoded into raw, hexadecimal and converted into audio. The noise translates into something uncanny, a descending tone, followed by a single low-frequency thud, like a door closing, and then nothing. No echo, no trace, just the cold background of the universe, unbroken and eternal. Somewhere in that silence, maybe something remains, an imprint of contact that outlived the light that carried it. Or maybe it was all coincidence, interference, reflection, human imagination reaching for patterns in chaos. But to those who heard the whispers live, the radio techs, the late-night astronomers, the handful of amateurs recording in their basements, one detail haunts them still. The noise didn't fade like static. It stopped, abrupt, deliberate, final, as if whatever was transmitting had simply turned its head and listened back. When 3IATLAS finally emerged from behind the sun, it was like watching a ghost come back with a wound it couldn't hide. The world's telescopes had been waiting, searching the edges of the solar glare for any glint, any movement. And then faintly, there it was, a shimmer where silence had been. But the object that reappeared was not the same one that vanished. The first to spot it was the solar orbiter's heliospheric imager. The return was quiet, almost embarrassed, its light curve weaker by half, its geometry distorted. The once vibrant emerald tail had faded to pale blue, shredded like cloth torn by unseen hands. The coma that had pulsed with internal motion before perihelion now hung still, dense, oddly compact. Astronomers described it as limping, not in literal motion, but in energy. Something inside the comet had dimmed. The brightness profile revealed the first clue. Before vanishing, Atlas had exhibited a consistent reflectivity ratio, what scientists call albedo, of 0.11, typical for dusty, ice-rich comets. After reappearance, that value dropped to 0.05, nearly half. For perspective, that's darker than asphalt. It was as though its surface had been scorched or coated in something non-reflective. Some speculated it had fused into glass under the sun's radiation. Others thought it might have shed its outer layer entirely, revealing a carbonized core that had never seen light before. But the strangest part wasn't its darkness, it was its calm. Most comets, after solar approach, erupt in fury, jets of gas, explosive outgassing, debris tails whipping in the solar wind. Atlas returned tranquil, almost inert. Its activity curve flattened. It looked less like a comet and more like an object that had stopped breathing. The trajectory analysts were first to raise alarms. The comet's path had shifted, subtly but unmistakably. When plotted against its pre-perihelion orbit, the outbound vector was off by nearly 0.12 degrees. That might sound trivial, but in cosmic terms, it's enormous, a difference measured in tens of thousands of kilometers. There was no gravitational explanation. The sun's mass, the planet's pull, even solar wind pressure, all accounted for. And yet, Atlas had deviated. The cause wasn't a push, it was a pull. Something, or perhaps some internal change, had redirected it. The comet was lighter, or hollowed, or magnetically altered. The orbital mechanics didn't lie, it wasn't just returning. It was reacting. Even NASA's Jet Propulsion Laboratory noted it in their bulletin. Observed outbound trajectory inconsistent with pre-encounter modeling.
Source of deviation indeterminate. Indeterminate.
A word used when data stops explaining and starts hinting. When light curve analysis resumed, another peculiarity surfaced. The object flickered, but not with the steady rotation of a tumbling body. Instead, it blinked irregularly as if rotating unevenly, or composed of fragments moving in sync. Fragmentation was the obvious culprit. But there was a catch. No debris was detected. None. No secondary bodies, no dust halo, no particulate trail. The comet appeared fractured yet whole, like glass cracked under stress, but still holding together through surface tension. Researchers proposed a phenomenon called partial coherence, a scenario where subbodies remain gravitationally locked by their own weak fields, orbiting an invisible center of mass. The same principle governs rubble pile asteroids, but never has it been recorded for a comet, much less one from another star system. If that's true, then 3IATLAS wasn't a solid traveler anymore. It was a cluster, bound by memory more than matter. The Hubble Space Telescope captured high-resolution imagery as soon as the sun's glare waned. The pictures showed a faint double helix pattern stretching along the tail, two parallel strands twisting, merging, then vanishing into diffuse haze. It was reminiscent of a DNA spiral. Coincidence, maybe. But plasma physicists noticed that the spacing between those twists matched the standing wave harmonics of electromagnetic flux tubes in the solar wind. In simpler terms, the tail wasn't just drifting, it was oscillating. Something was still pulsing through it long after the comet should have gone inert. Was it residual charge from solar exposure? Or was the object still interacting with the magnetic field, as if carrying an electromagnetic memory from its encounter? The data hinted at persistence, like a tuning fork still vibrating after the note has ended. Amateur astronomers joined the hunt, capturing long exposure images that revealed subtle patterns invisible to larger observatories. Some frames showed faint, concentric ripples emanating from the nucleus, rings of light like sound waves frozen in space. That discovery sent ripples of its own through the scientific community. Were those rings artifacts?
Camera noise.
Or were they real, shockwaves traveling through ionized dust? If real, then Atlas wasn't simply outgassing. It was emitting pulses, slow, expanding shells of charged material. That would mean its internal structure was still dynamic, capable of controlled release, and if it could regulate that...
What was regulating it?
Meanwhile, radio observations resumed. The mysterious 4.2-second signal that had haunted scientists during the blackout was gone, but not forgotten. Some still detected faint harmonics at the same interval, barely above noise level. It was as if the comet's voice had gone hoarse. When the signal was mathematically reconstructed using cross-correlation methods, a ghostly shape emerged in the frequency domain, a decaying harmonic ladder. It looked exactly like a dying carrier wave losing coherence. That realization unsettled even skeptics, because if 3IATLAS had been resonating, intentionally or not, with the sun's electromagnetic field, then its reappearance with a limp wasn't metaphorical, it was physical evidence of loss. Loss of charge, loss of signal, loss of something we don't yet have a name for. Then came the spectral surprise. When post-perihelion observations measured its chemical composition, something extraordinary happened. Nickel was gone. So was cyanide. So was water. Instead, faint traces of silicate vapor appeared, minerals usually found deep within planetary crusts. If true, that would mean the comet had exposed its internal skeleton, burning away everything volatile, leaving only core material. But the spectral lines didn't just show stone, they showed glass, silicate glass forms under intense heat, requiring temperatures far higher than a typical comet could survive. Yet Atlas was still intact. So how had it melted and lived? One speculative model proposed that the comet's interior underwent a phase shift, transforming crystalline ice into a supercooled liquid glass before re-solidifying in the sun's shadow. That process could create a self-insulating shell. Essentially, the comet remade itself. In that sense, reappearance with a limp wasn't just poetic, it was accurate. It came back weaker, darker, but evolved. By now, public interest had waned. Other celestial events stole the headlines. But within the private exchanges of observatories and data labs, unease lingered because something else didn't add up: its velocity. The comet should have slowed after solar passage, losing momentum from sublimation. Instead, it moved faster, slightly, but unmistakably. Calculations showed an increase of 0.07 kPa, too small for propulsion, too large for error. Where did the energy come from? Some theorized an internal venting of trapped gas, a delayed release acting like a microthruster. But that should have spun the comet, not propelled it evenly. The acceleration was linear, almost as if something inside had realigned its center of mass, like a gyroscope correcting itself after a hit. And that's when a new hypothesis formed, whispered in the corridors of speculative physics. Maybe 3IATLAS didn't just survive the sun, maybe it synchronized with it. The idea was radical. If the comet contained materials capable of magnetic resonance, say paramagnetic nickel alloys or superconductive compounds, it could, in theory, have absorbed part of the sun's magnetic pulse and stabilized around that frequency. That would explain the tail's helical shape, the oscillating light, the rhythmic pulses. It might even explain why its outbound path deviated. The object could have become magnetically polarized, subtly tugged by interplanetary field lines. It would also mean the comet's transformation wasn't random, it was responsive. And maybe, in some unfathomable way, intentional. By the time it exited the solar inner system, 3IATLAS had become a different kind of traveler, slower, darker, quieter. Its tail was no longer a beacon, but a scar, trailing wisps of pale dust that flickered like faint afterglow. The object's motion grew smoother, more stable, almost deliberate, as if finding a new rhythm in the darkness. Somewhere beyond Mars, it crossed the heliospheric current sheet again, and instruments recorded one final blip, a solitary magnetic pulse echoing the same 4.2-second cadence. Then it vanished from all detection. No reflection.
No emission.
No trace, just a trajectory line that pointed outward into the abyss. For most, that's where the story ends. A comet passed, transformed, and disappeared into the dark between stars. But to those who study its light curves, its missing signals, and its fractured reappearance, something still lingers. The sense that Atlas didn't merely endure the sun, it communed with it. That somewhere within that blinding proximity, it changed in ways beyond physical understanding. It returned, yes, but not whole.
Not broken either.
Something in between, something aware. It came back limping, 'cause maybe for a moment it walked. The timing couldn't have been better or worse, depending on who you ask. Just as 3IATLAS limped back into view, diminished and darkened, another comet suddenly blazed across the sky, C2025L3, Lemon. Bright, photogenic, predictable. Everything Atlas wasn't. Within hours, the headlines shifted. New bright green comet dazzles astronomers. Lemon lights up the northern sky, a once-in-a-lifetime view. The public, hungry for spectacle, moved on instantly. But the timing was uncanny, so perfect it almost felt scripted. Because Lemon appeared exactly when 3IATLAS re-emerged from behind the sun. And for the first time in the record, two comets from vastly different origins were not just visible in the same sky, but sharing the same heliocentric longitude. In cosmic terms, they lined up. And from that moment on, Atlas stopped being the story. It became a footnote. It wasn't just the media that shifted. The scientific focus did too. NASA's SOHO and ESA's solar orbiter both pivoted their observation schedules. Their sensors were recalibrated to track Lemon's photometric output instead of Atlas's weakened return. Data requests about Atlas were delayed, labeled non-priority. The reasoning was logical. Lemon was brighter, easier to study, and posed no telemetry risk from solar interference. But for some, it felt like an engineered handoff, a cosmic sleight of hand. The object that had confounded scientists with its unearthly nickel ratios, magnetic pulses, and mysterious disappearance suddenly faded into bureaucratic shadow. Meanwhile,
Lemon, stable, well-behaved,
and beautifully green, took center stage. And as one researcher put it in a private email later leaked online, it's as if the universe rolled out a decoy. To understand why the timing raised so many eyebrows, we have to rewind. C2025L3 Lemon had been catalogued months earlier, faint and unremarkable. Its orbit was highly elliptical but conventional, and its projected brightness barely grazed visibility. Yet right as 3IATLAS entered solar conjunction, the point where it vanished behind the sun, Lemon's luminosity curve spiked tenfold. For no clear reason. In other words, it switched on. Sound familiar? The same phrase had been used months earlier to describe Atlas itself, when it inexplicably brightened far from the sun, as though something inside had awakened. Now another comet was doing it. At the exact moment Atlas disappeared. Coincidence? Maybe. But coincidences don't usually carry this much symmetry. Lemon became a darling of the press. Its coma shimmered neon green, a result of diatomic carbon reacting with sunlight, a chemical glow common but photogenic. News outlets flooded the internet with long exposure images, each captioned like celestial postcards. Meanwhile, attempts to observe Atlas were quietly failing. When its coordinates were finally updated, telescopes aimed at its trajectory returned nothing but noise. It had faded below the visual threshold, or maybe something else was interfering. In multiple observation logs, researchers reported that when tracking Atlas's coordinates, data bandwidth dropped sharply, remote instruments lagged, radio links crackled, and image frames failed to sync. It was dismissed as solar wind interference. But Lemon's feeds, observed from nearly identical angular proximity, showed no such disruption. It was as if something didn't want Atlas seen, or worse, something was using Lemon's brightness as camouflage. The distraction effect isn't a new concept. In information theory, it refers to the sudden redirection of focus by introducing a high-signal event near a low-signal anomaly. The human eye and mind gravitates to brightness, to movement, to whatever demands attention, and the cosmos, it seems, knows that too. During the same window when Lemon captured the world's gaze, a faint magnetic anomaly was recorded by NASA's MAVEN probe orbiting Mars. A pulse, brief, symmetrical, matching the 4.2-second harmonic once linked to Atlas's strange emissions. That signal was never repeated, but its timestamp overlapped precisely with Lemon's peak luminosity. For those watching closely, it felt less like coincidence and more like choreography. A few fringe astronomers began to speculate publicly. They noticed that Lemon's green glow was unusually stable, its light curve unnaturally smooth. Normally, comet brightness fluctuates as jets of gas burst from different angles, creating micro-flickers in intensity. Lemon didn't flicker, it hummed. Spectroscopic analysis revealed a dominant emission band at 518 nanometers, expected for carbon, but strangely coherent, meaning the light waves were aligned in phase. Natural light doesn't behave like that. Laser light does. Of course, no one suggested Lemon was firing lasers, but it raised an uncomfortable question. Could the same phenomenon that made 3IATLAS switch on have somehow transferred to Lemon? Could it have been contagious? Then came the photographs, the ones that didn't make it to press. In a sequence captured by the European Southern Observatory, Lemon's tail exhibited an odd double structure, one faint, one bright. The dim tail appeared to bend toward the sun instead of away from it, like a magnetic tether. The brighter one, full of ionized dust, curved in the opposite direction. Between the two, a faint gap pulsed with light at precisely 4.2-second intervals. When analysts compared those intervals to Atlas's pre-vanish oscillations, they matched perfectly. The same rhythm now appearing in a different comet entirely. And suddenly, the theory shifted. Maybe Lemon wasn't the distraction. Maybe it was the receiver. If Atlas had indeed interacted with the sun, absorbing, amplifying, or transmitting something, then Lemon's sudden brightening might have been the echo, the aftershock, like two tuning forks vibrating at the same frequency. Even when separated by space, it's speculative, yes. But electromagnetic coupling between distant plasma bodies isn't fantasy. It's physics. Magnetic reconnection events in the solar wind can link objects across millions of kilometers through shared field lines. If Atlas became magnetically charged during its perihelion blackout, and Lemon's trajectory intersected those solar field lines days later, then Lemon might have been momentarily lit by that residual energy. An energy bright enough to blind every eye just as Atlas returned, dim and wounded. The universe's oldest misdirection: show them the light, hide the truth in the shadow behind it. But the story doesn't end there. Weeks after Lemon's peak visibility, something began to change. Its perfect symmetry started to distort. The once stable coma began flickering. The 4.2-second pulse weakened, stretched, then fractured into static. Its tail split in two directions, a literal divergence in its light path. To most, it looked like a natural fragmentation. But to those who'd tracked both comets, it looked eerily familiar. It was the same pattern Atlas displayed before its disappearance. The same rhythm, the same exhaustion. Lemon was repeating the cycle, like a sequel destined for the same ending. Then abruptly, Lemon dimmed. Its core brightness dropped by 80% in less than 36 hours. When astronomers attempted to photograph it, they found something chilling. The surrounding region of space had become opaque to radio frequencies. Observatories reported blank feeds, their sensors momentarily blinded, not by the sun, but by silence. And when the blackout ended, Lemon had changed orbit. Its new path veered slightly inward toward the sun, an improbable shift, considering it should have been moving outward. It was as if something had pulled it back or called it home. The idea of a cosmic relay, one object handing off to another, sounds like science fiction. But plasma astrophysicists quietly discuss it under a different name: coherent field coupling. It's the process where charged bodies synchronize via magnetic flux, allowing energy to transfer invisibly through the solar wind. If that's what happened, then the distraction effect wasn't merely observational, it was functional. Lemon didn't just distract human eyes. It may have masked an energetic event, a continuation of whatever process 3IATLAS began behind the sun. In that sense, the distraction wasn't about hiding Atlas from us. It was about hiding what Atlas was doing. Months later, when the excitement died, Lemon faded into the archives of ordinary comet history. No anomalies officially reported, no mysteries mentioned. But in a handful of private observatory notes, the story continues. Somewhere near the edge of the inner system, long after Lemon dimmed beyond visibility, a faint magnetic pulse was recorded again, barely detectable, repeating every 4.2 seconds, not from Lemon, not from Atlas, but from somewhere between them. An invisible midpoint, a relay station no one can see. And maybe that's what the distraction was really for. Not to make us look away, but to make us look elsewhere, while something ancient, silent, and patient continued its work in the space between. When 3IATLAS disappeared behind the sun, the world assumed it would return as it always had, dimmer, scarred, but visible. Yet when the data came back, something else was missing.
Not the comet.
Not entirely, but the proof that it had ever behaved the way scientists claimed it did. Images were gone, telemetry corrupted, spectral logs rewritten. Whole hours of solar observation wiped from the digital record, and for the first time since the object's arrival, there was no consensus on what had truly happened. Because while Atlas had vanished from sight, something far stranger had vanished from history. The first signs of quiet erasure came weeks later, when independent researchers tried to compile raw datasets from public archives, files that once displayed clear frames of the comet's pre-perihelion pulse now returned error codes or blank placeholders. In NASA's SOHO archive, the metadata still existed, timestamps, exposure lengths, even file names, but the contents were null. When requests were filed for backups, the official response was that data integrity loss occurred due to proton saturation during solar maximum activity. It was plausible. The sun had been restless, but the same corrupted frames were intact in third-party databases only days before. They were fine, until they weren't. Meanwhile, European observatories that had mirrored the same datasets began reporting checksum mismatches, a technical term for data that's been altered, not destroyed. It wasn't a hardware glitch. The information had changed. To the naked eye, the difference seemed trivial. Brightness values shifted, noise patterns smoothed, pixels recompressed. But in the world of astronomy, those microscopic changes mean everything. It was as if the universe itself had been retouched. The deeper the investigation went, the stranger it became. Spectral charts that had once displayed Atlas's signature nickel emission now ended abruptly at the iron line, as though the instruments had never detected anything unusual. Photometric logs showed no oscillations, no pulsing, no irregular periodicity. To anyone encountering the data for the first time, 3IATLAS looked perfectly normal, another unremarkable comet, but those who had studied it before the blackout knew better. They had seen the patterns, the anomalies, the flickers that shouldn't have existed. And now those traces were gone. Dr. Helena Wirth from the Max Planck Institute put it bluntly in a private correspondence. It's as though the event was rewritten to fit a model the universe could live with. The possibility of data tampering wasn't far-fetched. Space agencies regularly compress or reformat images to conserve bandwidth. But this was different. This looked intentional. In multiple archives, the same frames were replaced with duplicates, identical in timestamp, nearly identical in structure, but with one telling difference. The comet's nucleus had been shifted by exactly 1 pixel. 1 pixel may not sound like much, but across astronomical scales it represents hundreds of kilometers. It was as though someone or something was moving 3IATLAS, not in space, but in time. And then came the oddest discovery of all. The checksum for the altered frames didn't just differ from the originals. They matched future timestamps, data that shouldn't have existed when the event was first recorded. That means the replacements were inserted after the fact. Someone went back and changed history. When confronted with the inconsistencies, NASA's data systems team issued a short statement. Due to redundant mirroring protocols, files may appear re-time-stamped during archival synchronization. It was technically true, but synchronizations don't rewrite spectral lines. They don't erase specific chemical traces while leaving others untouched, and certainly they don't fabricate new noise patterns that perfectly overwrite known anomalies. So if it wasn't an accident, what was it? Theories began to divide the scientific community. Some argued that the interference came from the Sun itself, that the storm of charged particles near Perihelion had corrupted memory sectors in global systems simultaneously. Others whispered of a cover-up, a decision to hide something that couldn't be explained without igniting panic. A third group, the smallest but loudest, believed something far more radical, that the data wasn't deleted at all. It had been absorbed. Consider this. The missing hours of solar telemetry correspond precisely to the period when Atlas was hidden behind the Sun. During that same window, magnetometers on Earth recorded transient electromagnetic disturbances, brief, synchronized flickers lasting milliseconds. These weren't power surges or hardware faults. They were external, pulses faint but structured, arriving through the ionosphere. Now imagine a signal so powerful, so coherent, that it imprints itself onto digital systems not as noise, but as code, rewriting bits invisibly, like a ghost scribbling over reality's hard drive. Could Atlas have transmitted something that the world's instruments interpreted as its own corrections? Could the act of observation itself have been overwritten? That question haunts astrophysicists to this day, because in the weeks that followed, even physical evidence began to blur. Meteor streams that should have corresponded with Atlas's debris failed to appear. The expected dust trail never intersected Earth's orbit. Radar imaging of its predicted path came back clean. It was as though the object had taken everything with it, not just fragments, but proof that fragments ever existed, and yet faint traces remained, not in the sky, but in our systems. During the blackout, deep space tracking servers registered microsecond desynchronizations, small temporal hiccups where timestamps jumped backward. In one instance, a tracking server in Madrid briefly recorded negative time, meaning the data packets arrived before they were sent. Impossible, unless the source was outside conventional space-time. Whatever passed behind the sun didn't just vanish, it bent the rules that define what vanishing even means. That's when a new kind of silence began, not absence, but avoidance. The agencies stopped talking about Atlas altogether. Official bulletins referred to it in the past tense, as if it were already gone. Missions that once monitored its trajectory reclassified it as lost. But internally, observatories kept receiving encrypted update files, marked 3IATLAS continuity feed. Each one was tiny, a few kilobytes, and contained nothing but binary static. Yet when decoded, those binaries formed patterns that resembled the same 4.2-second harmonic spacing found in the comet's pre-vanish spectrum. The ghost was still whispering through corrupted code, and someone, somewhere, was listening. Meanwhile, a quiet audit revealed something chilling. Certain data sets weren't deleted by accident. They were deliberately quarantined. NASA's internal archive logs labeled these missing entries under a new category: External Protocol Lockout. It's a classification used when data is restricted by an external source, typically defense contractors or international partners, but the listed source wasn't human, it was blank, a digital void where an origin tag should be. That entry has never been explained. It's possible, of course, that all of this is coincidence, the product of faulty equipment, compression errors, or bureaucratic red tape. But coincidences don't synchronize across continents. They don't rewrite timestamps, and they certainly don't leave harmonic fingerprints that repeat every 4.2 seconds, the same interval that defined Atlas's heartbeat. The more the data disappeared, the more it looked curated, like someone tidying the stage after an experiment. So what truly vanished? Was it the object, the interstellar wanderer burned to ash in the sun's gravity well?
Or was it the evidence? The records, the measurements, the trail of breadcrumbs leading to something the universe didn't want archived?
If the latter is true, then perhaps 3IATLAS didn't die at all. Perhaps it crossed a threshold, one that rewrote its own record as it went, a kind of self-redacting phenomenon, erasing its fingerprints as it escaped, and maybe that's why every trace of it, from the radio whispers to the spectral lines, keeps fading.
Not because it's gone,
but because it's still moving not through space, but through memory, like an idea that deletes itself once understood. In the end, 3IATLAS leaves us with a riddle. Did we lose the comet, or did the comet lose us? Maybe both, because somewhere behind the sun, a moment existed that our records can no longer hold, an interaction so precise that even our machines forgot how to remember it. And if that's true, then the silence that followed wasn't an accident. It was a design, a closing of the book before we ever saw the last page. So what vanished? The object or the evidence? Maybe they're the same thing, because sometimes the only way to hide the truth is to make it forget itself.